A very good morning to all of you. I cordially invite you all for this engineering thermodynamics course. So today's classroom discussion topic is numerical problems on the dual cycle, air standard efficiency and mean effective pressure. So the motivation for the today's class is it is important to predict the performance of a dual cycle, and the outcome of the today's lecture is so you should be able to solve some numerical problems on the dual cycle. So in the previous class we discussed about the dual cycle working principle and how can we represent the dual cycle on PV diagram as well as in the TS diagram, and similarly how can we find out the air standard efficiency and mean effective pressure of the dual cycle. So in the today's class we will solve some problems on the dual cycle. So let us take the first problem. So an oil engine working on the dual combustion cycle has a compression ratio of the 14, that is the R value is given as the 14, and explosion ratio obtained from an indicator card is 1.4. So if the cutoff occurs at 6% of the stroke, find the ideal efficiency, take gamma for air is equivalent to 1.4. That is the similar problem is solved in the diesel cycle also. When the cutoff occurs at the 6% of the stroke, the same thing is repeated. So here write down the given data first. So compression ratio R is equivalent to 14 and the explosion ratio is given as the beta value is equivalent to 1.4, and the cutoff ratio he has given that is the 6% of the stroke. So rho minus 1 by is a gamma minus 1, that is a formula for the percentage of the cutoff ratio. So it is from this particular one we are able to find out the rho value is equivalent to 1.78. And in the previous class we derived the equation for the air standard efficiency of the dual cycle. So from this just you substitute what are the given values. So we are able to find out the dual cycle efficiency as 61.4%. So similarly, so this is the always I am telling you whether it is auto cycle or diesel cycle or the dual combustion cycle, whatever the cycle it may be, whenever a problem comes on any cycle, so first of all you have to represent the property diagram. So that particular property diagram, whether it is convenient to you, so whether if you draw the PV diagram or TS diagram, whichever is convenient to you. So basically the dual cycle is a constant volume heat addition partly and constant pressure heat addition partly. So that's why the representation of the dual cycle is must on the PV and TS diagrams. So let us go to the next problem of the dual cycle. So just you can see here, so this problem was given in the UPSC 1997, that is the Union Public Service Commission, that is IES examination. This particular problem is given. So read the problem very carefully and write down the given data. An IC engine operating on the dual cycle. So you know that dual cycle is also known as the limited pressure cycle. The temperature of the working fluid at the beginning of the compression. So this is the first you plot the dual cycle. At the beginning of the compression means at the point number 1. So at the point number 1 he has given it has 27 degrees centigrade. So convert into Kelvin. So it is the 300 Kelvin. The ratio of the maximum and minimum pressures of the cycle is 70. So from this particular one we are able to know that P3 is equivalent to P4. So it is the maximum pressure and the minimum pressure is the P1. So the maximum pressure to the minimum pressure is nothing but is a P3 by P1 or P4 by P1, because P3 is equivalent to P4. So P3 by P1 is equivalent to 70 and the compression ratio is 15. So compression ratio is 15. So here the compression ratio is nothing but is the V1 by V2. So V1 by V2 is equivalent to 15. So the amounts of heat added at constant volume and constant pressure are equal. So that is Q2 to 3 is equivalent to Q3 to 4. So that is the condition he has given. So now he is asking us, compute the air standard thermal efficiency of the cycle. State 3 main reasons why the actual thermal efficiency is different from the theoretical cycle. So now first let us consider the process 1 to 2. So from which you calculate the unknown temperature values. So T2 value you predict it as 886.2 Kelvin, and similarly you find out the unknown pressure values. So first of all we are finding out the unknown pressures and temperature values. So then we are simply substituting in the main equation of the dual cycle. So air standard efficiency is equivalent to work done by the heat supplied. So work done is nothing but heat supplied minus heat rejected. So whenever you are substituting all these parameters into this particular equation, so we are able to find out the dual cycle efficiency as 65.3%. It is one part of the answer. And the second part is also asking just you mention some of the reasons why the actual thermal efficiency is basically different from the theoretical value. So the one of the reasons I have listed down here. So in theoretical cycle, working substance is taken as air, whereas in the actual cycle, air with fuel will act as a working substance, because normally these are known as the air standard cycles, which is the Otto cycle, diesel cycle, and the dual combustion cycles. So we have taken only the air as the working fluid for the ideal purpose. But whenever we are dealing with the actual purpose, so the engines will work only with air plus fuel. So that's why whenever we are considering the air plus fuel characteristics, automatically the working properties will change. So that automatically it will reflecting the efficiency values. So the second reason here I have mentioned, the fuel combustion phenomena and associated problems like dissociation of the gases, dilution of the charge during the suction stroke, etc., have not been taken into the account whenever you are dealing with the ideal gas behavior. So due to which there is a deviation from the ideal cycle efficiency to the actual cycle efficiency for any type of the cycles, not only dual cycle, it is basically valid for the Otto cycle and diesel cycle also. So in the today's class, we solved some problems based on the dual cycle related to the air standard efficiency and mean effective pressure. So in the next class, we will meet with some other classroom discussion topic. So thank you for listening this topic on the numerical problems on dual cycle. Thank you.